Okay, so we talk about a very cool data structure which is called heap, and this heap is I mean we will basically talk about heap sort, but heap can be taught totally independent from heap sort. So, basically heap is nothing to do with heap sort, but we use this heap, I mean basically max heap, to have a sorting algorithm, and that is called heap sort, but heap can be taught totally separate way, like for especially it is a priority queue implementation. So, basically what is a priority queue? So, basically a data structure implementation implementing a set S which is associated with a key. Each element in S is associated with a key, and it should support the following operation, supporting the following operation. So, basically you have a dynamic set S, and this S set, and each element in the S set is associated with a key. So, key is basically, we can say, if S is a record, say student record. So, student roll number. So, roll number could be the, so if this is the record, so this is the roll number of the student. So, this could be the unique key of X. So, each of this data, or we can say record, is associated with a key. So, key is the unique representation of that, say of that. So, each element of S is associated with a key, and it should able to perform the following operation, like so this is S set. The operations are basically what? Operations are basically insert. We should able to insert an element in S. So, these are the operation: insert. Okay, so this is basically we insert X into S. So, we insert X, a new record, the X is the key of that record, into S, new record with some key value in X. This is the insert operation, and there is a max operation, max of S. So, this is basically return the element whose key value is maximum, return the element of S with largest key value. So, we are looking for maximum element from this set. So, S is a dynamic set, every time. So, we should able to insert a new record, new key in this S, and we should able to find out, this is another operation, max operation. We should able to get the maximum of this set, maximum element from S, which is the largest key value. Okay. And we should able to do this, another operation is called extract max. Okay, it is telling us we should return the maximum and delete from the queue, delete from S. We should return the element, return the element of S with maximum key with the largest key value, and remove it from S. That is also important. So, extract max is we are extracting the maximum element, that is the max S, and we should able to remove that element from S. Remove means delete, and remove it from S. So, this is also important. So, extract max means we should able to get the maximum element maximum, we should able to get the element whose the key value is maximum, and we should able to remove that element from this set S. Okay. And another operation is increase key. So, it should able to, so this is telling us we should able to increase the, so we take a key value, we take a x, and we should able to replace its key value by the new key value k. So, that is the increase operation. So, it should go to that particular value and we should able to increase it this operation. Now, if this data structure, if suppose we have a simple, so we need a data structure for this. So, we need a data structure for S. So, that is our goal. So, we need a data, this is called priority queue implementation. So, we need a data structure for this S, okay, so that we can perform this type of query. So, for that heap is the data structure which we are going to introduce for this purpose. So, heap is basically, it is basically an array, but it is viewed as a completely binary tree, nearly complete binary tree. So, we just, so heap is basically, so heap is basically implementation of a priority queue. Of a priority queue. So, that S. So, heap is used to, so it is basically, it's basically an array which is viewed as a viewed or visualized as a, this is the viewed or visualized as a nearly complete binary tree. How? We will explain. Complete binary tree. Okay. So, basically it is an array, but we are viewing this array as a binary tree. Okay. How we can view a array as a binary tree? So, that we have to explain. So, suppose we have given a array. So, say we have a array. So, this is 16, these are the element, these are the key value 10, 8, 7, 9, 3, 2, 4, 1. So, how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, we have an array of 10 elements. Now, this array we want to view as a, we want to visualize this array as a tree. So, how we can do that? So, one way to do this is we start with this as a root. Okay, so, we start with this as a root. So, this is A1 and then A2, A3, then A4, A5, A6, A7, then A8, A9 and then we have A10 because array is up to 10. So, this is the way we view this array as a tree. So, this is basically A1, A1 is 16. So, we just put this value, this is the key values 10, 8, 7, 9, 3, 2, 4, 1. Okay. So, this is the visualization of this array as a tree, and this is nearly complete binary tree because here number is 10. If the number is say 15, if we have another 1, 2, 3, another 4 element in the array, if the array size is 1 to 15, then it is a complete binary tree. But anyway, this height of this tree is log n if there are n element. So, that is why it is called nearly complete binary tree. So, depending on the value of n, we will have complete or it is a nearly complete. So, this is a visualization of this array as a tree, and this is called heap. This visualization, this is called heap. but this is just a visualization. In reality, we do not have this tree. So, in reality, if we have to have the if we need to do the tree implementation, what we need to do? Suppose in C we want to implement tree. So, what we need to do? We need to define a structure, struct node, then we need to have the data or the key value, and then we need to have the pointers, struct node star left, star right, maybe star parent, something like that. Okay. So, this way we just implement a tree in a C language to have a this type, but here we do not need that. So, no pointer is required. This is the advantage. No pointer is required to have this tree, because we know if a node is say I. So, if this 3, so 3 node. So, who are the child for 3? 6 and 7. So, that means if a node is I, this is AI, this is I. If a node is AI, then we know the childs are at A to I plus 1. This is basically 2I plus 1. So, this is the formula we use to build to visualize that tree. This tree is our visualization. It is not there actually. We are not having this tree. We are not having the pointer to have this tree. We are just viewing this tree. Basically, we have an array, but we are viewing this tree that this 10 is the child of 10 is the parent of 9 and 3, like this. So, basically, we have an array, but we are viewing this as an array as a tree, and this is basically called heap data structure. So, this is the A to I and A to I plus 1. Okay. So, this is the formula we use for visualizing the tree. So, no pointer is required. So, we know where are the child. So, basically left of I is 2I and right of I is 2I plus 1. So, this is the formula will give us the tree, and the parent of I is basically I by 2. Okay. So, by using this formula we will just view this as a tree. Okay. So, this is called heap. This array is called heap, where we are viewing this array as a binary tree, nearly complete binary. So, if there are n element, height of the tree is, so height is basically order of log n. So, that is why it is a good tree. It is a balanced tree. We will talk about balanced tree. So, balance means the height is order of log n. So, that is why it is a good tree. So, we can view this as a tree. So, this is called heap. This data structure is called heap. Okay. Now, when we call this heap as a max heap, so we call this heap. So, this is the way we just have child. Okay. So, if you take this is as a I, then we know that the childs are basically 2I plus 1. So, 2I, there is no 2I plus 1. So, this 7 has only one child, which is 1. Okay. So, this is basically the formula to get to view this tree. Okay. So, now we call this heap to be max heap. So, when we say, so this is 3. So, let us have this. So, this is basically the visualization. Actually, we have this array. Okay. So, let us have the array. So, the array is 16, 14, 10, then 8, 7, 9, 3, 2, 4, 1. Okay. 16, 14, 8, 7, 9, 3, 2, 4, 1. This is the array. Okay. Okay. So, when a heap is called max heap, the definition of a max heap is if each of the element is greater than from its child. We take an element, this is the element, say ith element, if it is greater than from its child. So, for 8 the childs are basically 2i plus 1. So, these two. So, if every element, if every array element is greater than or equal to from its child, every element, and if this is true for every element. So, that means if this is ai, so if this is ai, ith element, then the child is basically where a to I and a to I plus 1. So, that means if ai is greater than equal to maximum of a to I and a to I plus 1 for all I, and if this is true for all I, then every element is greater than from its child. Then we call, and if this is true for all I, this is the symbol for all. If this is true for all I, then we called our heap is max heap. This is the definition. So, for max heap this property should be there, every element should be greater than from its child. So, is this a max heap array? So, we can verify that. So, we have to check every element whether it is greater than from its child. So, if we take this, this is having no child. So, this element is greater than from its child, this element is greater than from its child, this is also greater than from its child, this is also greater than from its child. So, this is a max heap array. Okay. So, this array is a max heap array. So, okay. So, this is a max heap array. Now, question is, given a array, so in general we may not have a max heap array. So, given a array, suppose we take a input, say suppose instead of this say this is 14. So, instead of 14 suppose we have 9 already, we have 11, we can put 11 somewhere here. So, instead of 16 suppose this is 11. So, if this is 11, then this is not a max heap array, because this element is not greater than from this. So, now the question is, given a array, how we can make a array to be a max heap array. So, what is the advantage of having max heap array? So, advantage is, if we have a array which is max heap array, suppose this one, then we know root contain the maximum element. So, that max operation we can easily find out. So, we should able to perform those queries, na, max query. So, max of S. So, this set is basically S. Okay. So, max of S is basically maximum element. So, this is basically root. This is the basically A1 if it is if the array is a max heap array. Okay. Similarly, we can have min heap array. In that case, the minimum is our priority. So, min priority. So, we will talk about that. So, if you have min priority, then we have the min heap. In the min heap, the property will be all the elements will be less than from its child. So, that will be the min heap property. Okay. So, now the question is, so in general we have an unordered array, we have given any array, how we can make the array to be max heap array, or after how we can extract the max, I mean how we can delete it from this array and again make the array to be max heap array. So, those operations we have to do. So, we have to perform few heap operation. So, those are basically max heapify and build max heap. So, these are basically heap operation. Okay. So, basically build massif so this is basically the function which will produce a massive array from another array. We have given an array and we have to make it massive array, and that will be done by this subroutine build massive by this function. So, build massive is the function or the subroutine which will take the input as any array and it will produce the massive array. We will talk about this function, this subroutine. And in this build massive, we need to take help of another function, another subroutine which is called maxify. So, you can write small or bigger, anyway we should be consistent. Maxify. So, maxify means it should able to correct only one violation, correct a single violation. I will explain. Violation of heap property, especially maxif we are talking about, it could be miniv also, heap property in a subtree at its root. Okay. So, this is a subroutine. This is a subroutine which we are going to call in this build massive, and this maxify is basically so this is say ith element. So, maybe we have to call this maxify of the array at the point I. So, this is the call. So, we will talk about the code for this. So, we will see how this will looks like. So, this is the maxify. So, we call this maxify at the point. So, for that what we need to have, so this is the left element, left child, this is the right child. So, this is the left subarray, this is the right subarray. So, for this maxify we assume everything is okay over here and everything is okay over here. So, this subarray is already maxify and this subarray is also maxify, only we may have a violation at this point. So, that is why it can only handle the single violation. So, maxify can only handle the single violation. So, that means everything is fine over here, everything is fine over here, only we may have a problem with this point. So, then only we can call this maxify. This assumption is very much required to call this maxify. So, whenever we call the maxify at that point, this assumption should be there that we have to check that whether everything is okay in the left subarray, everything is okay in the right subarray, then only we will call maxify. See, this maxify can handle single violation. So, that is very important. So, we will talk about maxify, how it will handle this violation through an example. Suppose we have this is suppose a given input say. So, we have 4, 10, so 14, 7, 9, 3 and say we have 2, 8 and 1. Okay. So, what is the array? Array is 16, 4, 10, then 16, 4, 10, 14, 7, 9, 3, 2, 8, 1. So, this is the given array. This is the array. This is the array and this is the 1, 2, 3, these are the indexes 4, 5, 6, 7, 8, 9, 10. So, there are 10 elements. Okay. Is this a massive array? We can just check whether each element is greater than from its child. this is greater than from its child, this is greater than from its child, this is greater than from its child, this is but this is not greater than from its child. So, we have a problem over here. So, we have to call this maxify, and for calling the maxify you have to check whether everything is okay over here, everything is okay over here. This is the left subtree, this is the right subtree. If we just check, this is already maxify, this is already maxive subarray, this is also maxive subarray. So, then only we can call the maxify at this point. So, that is the assumption we need to have. So, we call the maxify on A at 2, I is equal to 2. Okay. So, we call this maxify at this point, this is 1, 2, 3. So, this is the point we call the maxify. Remember, this tree we are just visualizing, mainly we have this array and we can view this array as a tree. Okay. So, now how we can fix that? So, maxify subroutine is work like this. So, this has a problem. So, what we do? We replace this by the maximum of these two. So, these are the two child. So, among this 14 is the maximum. So, we replace 14 with this 4. So, this 14 will, so this is 14, now 4 will come here and the 14 will go here. Now, once we put this 4, then it may violate. So, again we have to call the maxify over here. So, we call this maxify, it may violate A, and where it is going? It is going to 4. We call the maxify at the point 4. Now, again we check, this is already maxify, this is already maxify. So, we may have single violation. Yes, there is a violation because this is less than 8. So, what we do? Again we just replace this by maximum of these two. So, this is maximum. So, this will come 4 and this will be 8. So, now this is the leaf node. So, we stop. So, this is the maxify operation, maxify subroutine. So, we keep on doing until we reach to a leaf node or it is fixed. So, but every time we have to remember this is can handle only single violation. So, every time we need to check whether left part is okay, right part is okay. We may have a violation in that corresponding root. Okay. So, this is very much required to have, and then what is the time complexity? So, it may go up to the height. So, if there are n nodes and if we are starting from the root, then the time complexity may be the log n for the maxify. Okay. So, it may go up to the height. So, we will use this maxify to build the a maxive array from a unordered array. So, that will be the build maxive we will talk about in the next class. Thank you.